audible to you? Can you hear me?
Yes, sir.
Right. So today's class, I will take up some problems. Heat transfer is basically full of numericals, a bit of theoretical derivation and numericals, and your concepts will be much clear once you solve some numericals. And as I always insist, if you have taken any of my earlier classes, I always insist that whenever you solve a numerical problem, you also draw a schematic diagram. Okay, so that kind of a diagram will actually give you a better understanding of the problem, and the physical implications, the physics behind the problem also will be clear to you, and also for anybody who is going through that solution procedure. Okay, so in today's class, I will take up some problems. So let me first share my slides with you. All right, so we'll start with this problem. So yesterday I have given a brief introduction of this problem. At any given instant of time, the temperature distribution within an infinite homogeneous body is given by the function as given. Temperature as a function of x, y, and z coordinates, that means spatial coordinates, are given. Assuming constant properties and no internal heat generation, determine the regions where the temperature changes with time. So uh, this is the problem in a three-dimensional steady state conduction with no heat generation and also with constant properties. Okay, so using this, we will have to determine, we are not actually told whether it's a steady state or not. So we have to find whether it is steady state or not. We have to determine whether the temperature changes with time or not. So according to this equation, at some point, at some instance of time, this is the temperature distribution. But at a different instance, will the temperature distribution be different or not is what we are supposed to estimate. Now, how do we do that? So, as I said in the previous class, the variation of temperature with respect to time is quantified by the term dou T by dou tau. So, if you can estimate this value dou T by dou tau, this value, the magnitude of this value will tell you whether the temperature is changing with time or not. So we have to estimate this. For that, we should use the general conduction equation. So you can see here, the first equation that we derived actually. So this equation in Cartesian coordinates, since we are given the temperature distribution in terms of x, y, and z, we can assume that it's in the Cartesian coordinates. So this is the three-dimensional heat conduction equation in Cartesian coordinates, including heat generation and including the time dependence of temperature. And you can see here the k is inside the brackets, inside the derivative dou by dou x. So if k is a constant, this can actually be brought outside. But since this is not a constant in this equation, it is treated as a variable, it is inside the bracket. But if it is a constant, as given in the problem, in the current problem, we can actually what to say, treat it as a constant and bring it out of the derivative. Okay, so before we try to solve the problem, we will look at how this particular equation can be simplified, and so that it is applicable for our problem. So we are told that it is having no heat generation. That means this term will be equal to 0. We are told that the property is a constant. That means this k will come out. This k also will come out. This k also will come out. All these three k's can be taken out, and we can write k outside and in these brackets. So we can actually, in further steps, we can take this k to the right hand side. So this can become rho c by k. Okay, so in this way we can simplify and then proceed with the solution. So I will demonstrate how to do that, especially. So we'll start with the most fundamental equation for this. We have the equation as dou by dou x of k dou t by dou x plus dou by dou y of k dou t by dou y plus dou by dou z of k dou t by dou z is equal to plus q dot is equal to rho cp dou t by dou tau. This is the most general equation containing everything that is possible. So when k is constant, this becomes dou square t by dou x square, dou square t by dou x square, or will not do it, will not expand it. We'll simply say we'll take the k out. Dou by dou x of, well, in fact we can write it dou square t by dou x square because this k comes out, plus dou square t by dou y square plus dou square t by dou z square plus q dot by k is equal to rho cp by k dou t by dou tau. When there is no heat generation, q dot is equal to 0. So we will have dou square t, okay, sorry, this k must not be here because I have taken it to the right hand side. Dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square is equal to rho cp by k dou t by dou tau. So this is the governing equation of the present situation, present problem. So from this, to answer the question asked whether the temperature changes with respect to time or not, we will have to evaluate this particular term. To evaluate this particular term, we should know the values of dou square t by dou x square, dou square t by dou y square, and dou square t by dou z square, and also if the values of rho, cp, and k. These values should be known. So anyway, in the problem we are not given the values of rho, cp, and k, but we will see. We will see with this term dou square t by dou x square and so on. So the temperature given to us is temperature as a function of the three dimensions is given as minus 2y z square minus xy. Okay, so using this equation, we can evaluate one of these terms. For example, dou square t by dou x square can be evaluated like this. First, differentiate this t with respect to x and then differentiate it again. So 2 times differentiating this equation will give you that value. So the next slide I will go here. I'll write dou t by dou x is equal to have x here and x here. So 2x minus y. Dou t by dou x will be 2x minus y. Similarly, dou square t by dou x square, that means differentiating this again will give you 2. Similarly, dou t by dou y, have y here minus 4y, and we have 1y here, minus 4y minus x 2yz. So we have y here also. So minus 4y minus x plus 2z. And dou square t by dou y square will be minus 4. Similarly, dou t by dou z will be z here and here. So 2z plus 2y. And dou square t by dou z square will be 2. Okay, so now we'll substitute these known values in the equation uh, we have derived. Dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square is equal to dou cp by k dou t by dou tau. Now dou square t by dou x square is 2 plus dou square t by dou y square is minus 4 plus dou square t by dou z square is equal to rho cp by k dou t by dou tau. Now this left hand side becomes 0 is equal to rho cp by k dou t by dou tau. Okay, so rho cp by k, there is a name for that. Do you remember what that is? Or it's actually k divided by rho cp. There's one symbol given to that group. Anyone remembers that name of that symbol? That symbol is, let me say, alpha. Okay, now the right hand side, for the right hand side to become equal to 0, the rho should be equal to 0 or Cp should be equal to 0. Usually any solid substances will have some density, some specific heat. So this cannot be equal to 0. So the only possibility is dou t by dou tau to be equal to 0. So you can write therefore dou t by dou tau is equal to 0. Okay. So this is what you get. So that means, to conclude, we can say that the temperature does not change with time at the given instance. So we are given some instance, at that instance we should know it doesn't change. So as I said, we should always try to draw a schematic diagram, but in this particular thing we don't really have any numbers to draw, but we know that it is a Cartesian plot, so we can try to draw it approximately. This is something like this: x, y, and z, and on this we have some surface plot will be there, which will be a representative of the temperature at that particular instance. So using softwares only, you will be able to meaningfully draw some temperature. So if you are good at MATLAB, you can actually plot this. You can imagine, or you can assume that x varies from x varies from 0 to 10. Similarly, y varies from 0 to 10. Z varies from 0 to 10. So using these coordinates, you can create a network, and you can compute the temperatures at all the points inside that network. So that will give you the temperature, which you can be able to plot on a surface plot. So that's about this particular problem. Do you have any questions related to this problem? Are you able to follow?
Yes, sir.
Okay, so see, the equation given is a simple equation which we could easily differentiate. But sometimes we may not be able to differentiate because the equation can be complex. If there are a lot of trigonometric functions and logarithmic functions and exponents in the equation, then differentiation can get difficult. In such a case, what we go for is what are known as numerical methods. So using numerical methods, we'll numerically differentiate it. We'll get an approximate answer, but as far as engineering applications are concerned, those approximate answers are good enough to draw some conclusions. So in that way, we usually proceed with solving some problems where the differentiation or integration is not straightforward. If we don't have direct formulas or some direct methods to integrate, then we will have to go for these numerical methods. All right. Now, we move on to the next problem. So here you have a, I'll create some two slides. Okay. So here I have is the steady state temperature distribution in a one-dimensional wall of thermal conductivity 50 watt per meter Kelvin, and the thickness is 50 millimeters. Okay. Sure. Okay. Yeah, yeah. So we have steady state temperature distribution in a one-dimensional wall of thermal conductivity 50 watt per meter Kelvin, and the thickness is observed to be T is equal to A plus B x square, where A is 200 and B is minus 2000 Celsius per square meter, and X is in meters. What is the heat generation in the wall? Determine the heat flux at the two wall faces. So this is the problem. So we are given the temperature profile, we are given the conductivity of the wall and also the thickness of the wall. So how to solve this problem? By looking at the thermal temperature distribution, T is equal to A plus B x square, can you tell whether whether the temperature distribution is linear or non-linear? Is it linear or non-linear? You see this x square is there. So which makes it non-linear. Okay. Now, before we actually go into finding out what is the heat generation wall, let us find out how the temperature profile looks like. Okay. I'll open an Excel sheet, and using that I'll try to evaluate the temperature profile. We have X, and we are given that X varies from from thickness of 50 millimeters. Okay, so x varies from 0 to 50. So I will plot at 1 millimeter interval. Temperature is given as a plus bx square. A is 200. B is minus 2000. Minus. So A is in millimeters. So I'll open a bracket. And I'll create another bracket so that now I will plot a graph. See, you can see here there is this non-linearity. Okay, so actually as x increases, the thickness is decreasing. Okay, now this is assuming that x starts from 0. Now, yesterday we have seen that for problems related to what you say heat generation, we have taken the midplane as x is equal to 0. Okay, so depending on that, the temperature profile may start here, but still you see at the midplane uh, you will still have that dt by dx is equal to 0. Okay, so this, if you plot the temperature profile, you will have an understanding of how things are, how things look, how the temperature looks like. Anyway, now that we are given the temperature profile, we are asked to find out what is the heat generation in the wall. Determine the heat fluxes at the two wall faces. Okay, so let us take up this problem. So we have a wall here. This is, we are told that this is 50 millimeters. Okay, now we are given K as 50 watt per meter Kelvin, and temperature is T is equal to A plus Bx square, where A also is given, A is 200, B is minus 2000. 100 minus 2000 x square. Remember, x is in meters, even though thickness is in millimeters. Remember, in this equation, x is in meters. How did I know that? Because you see from this. So what is the heat generation in the wall? Determine the heat fluxes. So for this, since we are told that there is a heat generation, we are asked to find, we will solve this one-dimensional heat conduction equation involving the heat generation. So I'll bring about dou square T by dou x square. Now the conductivity is constant. Therefore, I could actually bring the conductivity out. So this plus Q dot divided by K is equal to at steady state. So on the right, dou T by dou tau multiplied by rho Cp by K will be 0. So this will be 0. So this is the equation for one-dimensional heat conduction with heat generation. So this equation we have seen earlier also in the summary. I have given here somewhere. It's not in This is no heat generation. Here it is, the heat generation. Here, this equation. You have seen this equation. Okay, so this is the equation we have taken up and we are trying to solve. So the same equation. Now we have to find the value of q dot. That's the question. Okay, so if we know the value of k, if we can evaluate dou square t by dou x square using this temperature profile, everything will be quite simple. Okay, so now since in this equation temperature is depending only on x, this very well becomes d square t divided by dx square plus q dot by k is equal to 0. Okay, now dt by dx we can evaluate as a d by dx of 200 minus 2000 x square. So this will be minus 4000 x. Similarly, d square t by dx square. Let me differentiate this once again. What you'll have is minus 4000. Okay, so if you substitute this in this equation, you have minus 4000 plus q dot divided by k is 50 is equal to 0. So this implies q dot is equal to 50 multiplied by 4000 is equal to, this is 20, 1, 2, 3, 4. Watt per meter cube. Remember, this is the unit of heat generation. So this is simply written as 2 multiplied by 10 power 5 watt per cubic meters. So this is the rate of heat generation that is possible in this particular slab which is having the given temperature profile. Okay, so this is the first part of the problem. We could estimate the heat generation in the wall. Heat generation turns out to be 2 multiplied by 10 power 5 watt per meter cube. The second question is determine the heat fluxes at the two wall faces. So this wall has two faces, right? This is one face and this is the other face. So at these two faces, we are asked to find out what is heat flux Q by A here and Q by A here. The wall heat fluxes can be different. You can see here the temperature profile we have seen is different at the two walls. At the left side, the temperature was 200 degrees Celsius, and at the right side, it is about 195 degrees Celsius. The temperatures are different. So there is a possibility of different heat fluxes at these two ends. So to find the heat flux at this point, what we do is draw the schematic diagram for this. At this wall, let us say, on this wall, heat flux is, basically, you see, we saw that the temperature was something like this. That means there is actually heat transfer in this direction. Okay, so heat flux at this point, Q by A. So Q by A is equal to, at this in this control volume, heat enters the control volume in the form of conduction, and it leaves in the same direction. So Q by A is equal to, using the conduction formula, minus K dou T by dou X, or dt by dx, whatever. In this case, it's dt by dx minus K dt by dx. Now Q by A is nothing but the heat flux. So Q by A at at x is equal to 50 millimeters. This is, let us say, this is x measurement direction. So x is equal to 0 and x is equal to 50 if we are measuring like this. Then q by a at x is equal to 50 is minus k dt by dx. We have dt by dx somewhere. dt by dx is minus 4000x. Minus 4000x. So is equal to k multiplied by 4000x. This is a general formula. So if you substitute x is equal to 50 millimeters, so that will be k is how much? 50 into 4000 multiplied by x. X is 50 50 millimeters. So we can write it as 50 by 1000. So this will be how much is that? It's 10,000 watts per meter square. This is the heat flux on the right hand side. Now, similarly, we have to evaluate this is the heat flux 10,000 meters square on the right face. On the left face also we have to evaluate. So, Q by A, this is the heat flux at x is equal to 0 is again K multiplied by 4000x. So, this will be K multiplied by 4000 multiplied by 0. So, this is 0. So, heat flux on this side is 0. So, Q by A on this side is equal to 0. So basically what is happening is this particular wall is having a 0 heat flux. So there is actually no heat transfer. That means it is behaving as an adiabatic surface. So dt by dx at this point is 0. So if you try to draw the temperature profile on one side, what we have seen is 0, 50, temperature profile was varying like this. Now, if you want to extend this surface to the left hand side also, just an imaginary surface to the left side and plot the same temperature profile on the other side, you will have a mirror image of this. So this is a mirror image of this. That is because at this point there is no heat flux. That means this surface acts as an adiabatic surface, as if this surface is perfectly insulated. Therefore, there won't be any heat transfer on this surface. So here Q by A is equal to 0, which implies dt by dx is equal to 0. Okay, so this is how you can solve this problem. So we are given the temperature profile inside a cylinder, inside a surface, cylindrical, flat surface, a plane wall, and we are told that there is some heat generation. So based on that, we could evaluate the value of the heat generation. It turned out to be 2 multiplied by 10 power 5 watt per meter cube, and the heat fluxes on either side are 0 and 10,000 watt per meter square. Okay, so as I told you, usually we will be asked to find out the heat transfer. Sometimes the heat transfer expressed in terms of heat flux, and also we will be asked to find temperatures inside a certain region, inside a certain domain. So these will be the common questions asked. You should be able to find out these values in heat transfer, and whenever there is heat generation, you may be also interested in finding out what will be the rate of heat generation. Okay, so That's one problem which we can take up. All right, now we'll move on. Uh, Now this problem can take a little longer, and since we don't have enough time, I will move on to problem number 4. The problem number 3 I will take up tomorrow in the next class, on Thursday's class. So here you see there is a industrial, there is an industrial furnace is made of fire clay brick of thickness 25 centimeters and thermal conductivity 1 watt per meter Kelvin. The outside surface is insulated having material K of 0.05 watt per meter Kelvin. Determine the thickness of the insulation layer in order to limit the heat loss from the surface wall to 1000 watt per meter square when the inside surface of the wall is 1030 degrees Celsius. Okay, so it's a some detailed statement. Let us draw the schematic diagram, then we will understand. So there is an industrial furnace made of a fire clay brick of thickness 25 centimeters and thermal conductivity 1 watt per meter Kelvin. So let's draw the wall. So this is the wall. This is fire clay having a thickness of 25 centimeters. So this is 25 centimeters and K is 1. Outside surface is insulated with material having K of 0.05. So this surface, let us say this is the outside one, this is insulated, and K for this is, so this thickness is not known, we have to find out. There are certain conditions for that thickness to be determined in order to limit the heat loss from the furnace wall to 1000 watt per meter square. So this heat transferred here in this direction, this Q should be 1000 watt per meter square. So this is basically heat flux, Q by A should be 1000 watt per meter square. When the inside surface of the wall is 1030 degrees Celsius and the outside at 30 degrees Celsius. So this temperature is 1030 degrees Celsius and this temperature is simply 30 degrees Celsius. So we have to find what is this value of A, value of X. Okay. Now we know that this we'll say this T inside temperature is TIN is 1030 degrees Celsius. See, in this problem there is no radiation involved, so you can leave the temperatures in Celsius itself. But if there is radiation, then you will have to convert Celsius to Kelvin, and T out is given as 30 degrees Celsius. Okay, and this is a purely conduction problem, so therefore the Q is minus Ka dt by dx, or Q by A is equal to minus K dt by dx. And if you get rid of this minus sign, simply write K delta T by delta X. Okay. Now, for see, in between these two surfaces, there is some intermediate surface. This surface, let us say this surface has got a temperature T. As of now, we don't know the temperature. We'll call it T. So heat transferred from this point to this point should be 1000. That's the area. Since area is constant, heat flux from this point to this point is 1000, and from here to here also it should be 1000. Okay, so using any of these values, you can actually evaluate the intermediate temperature. So we'll take for the fire clay wall, Q by A is equal to K delta T by delta X, and Q by A is 1000. That's what is given in the problem. Is K is 1 multiplied by delta T. Delta T is 1030 minus the unknown temperature T divided by delta X, 25 centimeters. So this is 25 multiplied by 10 power minus 3. Is it 25 centimeters? Yeah, so it is 10 power minus 2. Or 0.25. So using this, you can actually find the value of T, the temperature of the intermediate surface. So this is 1000 780 degrees Celsius. This is the temperature. Okay. Now, whatever heat flux is on this wall must be the same as the heat flux on this wall. Why? Because this is a non-radial system. It is a plane wall. Therefore, the areas of this face, and this face are the same. Therefore, the heat transfer is the same and heat flux remains the same. But what happens in case of radial systems is that heat transfer will be the same, but as the radius changes, area also changes. Therefore, heat flux can be different. So that's a typical characteristic of radial systems. So since this is not cylindrical or spherical, we can very well say that the heat flux on the left face is same as the heat flux on the right face. So Q by A on the left side or inside is Q by A on the outside. So I will evaluate Q by A on the outside. Q by A on the outside is equal to Ka delta K, simply K delta T by delta X. Now Q by A is given as 1000 is equal to K, conductivity of the insulation 0.05 multiplied by delta T. Delta T, this T minus 0, T minus 30. This wall is 30 degrees, so T minus 30 divided by the unknown thickness X. Now this T is now known to us. This is 0.05 multiplied by T. We just divided by X. So from this I can find the value of X. So we can evaluate this. Point 0.0375 meters or 3.75 centimeters. This is a reasonable value of the insulation thickness that is possible. Okay. So this answers both the questions. We are asked to find the thickness of insulation. So that thickness of insulation turns out to be 3.75 centimeters. So why 3.75 centimeters? So that we maintain a outside temperature of 30 degrees Celsius. So that outside, when any person touches the outside surface, it's not burn his hands. So for that, if this temperature is allowed to be 50 degrees Celsius, then this insulation thickness will actually reduce. If this temperature is supposed to be 20 degrees Celsius, then this thickness will increase. So in that way, this problem will change. Okay. So these are some of the problems we can solve in this. We will also continue again further with the similar problems in the next class also. On Thursday also, I'll solve some problems. Again, we'll extensively use the data book on Thursday. So be prepared. Come with your heat and mass transfer data books. All right.
Excuse me, sir.
Yes.
Sir, why are we not taking the units in Kelvin, unlike the previous numericals in other courses we have done, where we took the temperature as Kelvin?
Yeah. See, in 99% of the cases, if you take the temperatures in Kelvin, you will be extremely safe. Okay, it's a good practice to use the temperatures in Kelvin. But since in the problem the temperatures are given in Celsius, and if you are lazy, and you can very well go ahead with using temperatures in Celsius, because as far as the temperature differences are concerned, you see in all this heat transfer, the temperature difference is what is more important. Delta T, dT by dx, or HA delta T. The temperature difference is important, and temperature difference in Kelvin and in Celsius is the same value. So that is why it doesn't matter when you are talking about the temperature differences, it doesn't matter whether you solve the problem in Celsius or in Kelvin. But when it comes to radiation, we deal with the temperature raised to the power 4. There, by definition, the equation is in itself in Kelvin. So there you will have to convert it to Kelvin. So if you have radiation, as I said earlier, if you have radiation, better convert all the temperatures to Kelvin. Otherwise, you can take the liberty of continuing with temperatures in Celsius and still be correct. Okay?
Yes, sir.
But it's a good practice to always convert it to Kelvin.
Okay, sir.
Now let me take your attendance. Mrutunidhi,
Present, sir.
Ilash,
Present, sir.
Jarian,
Present, sir.
Sudan,
Yes, sir.
Dilip, Karth,
Sir Pranav Dilip present, sir.
Karth,
Siddharth, sir.
Devatsan,
Present, sir.
Mitrayan,
Present, sir.
Ranivel,
Present, sir.
Anant,
Present, sir.
Kalagan,
Present, sir.
Niranjan,
Present, sir.
Karan,
Present, sir.
Menon,
Present, sir.
Kritik,
Present, sir. Present, sir.
Praveen,
Present, sir.
Adil Sinju,
Present, sir.
Teddy,
Present, sir.
Present, sir. Chintan present, sir.
Hamza Hassan,
Present, sir. Hamza Hassan present.
Ayush Tripathi,
Present, sir.
Harshvardhan,
Present, sir.
Hemant Kumar,
Yes, sir.
Vishwa,
Present.
Chandramouli Singh,
Present, sir.
Subwania,
Present, sir. Present, sir.
Sai Rohit, Sri Raman,
Present, sir.
Kal,
Yes, sir.
Deepesh, Venkat,
Yes, sir.
Kumaran,
Present, sir.
Sundar Krishna, Pranav, Jayanti,
Sir Pranav present, sir.
Jayanti,
Present, sir.
Sriniket,
Present, sir.
Badri Narayanan,
Sir, Badri Narayanan present, sir.
Ajit,
also present.
Ajit present, sir.
Harish Raghav,
Present, sir.
Rahul,
Present, sir.
Firoz,
Sir, Firoz present, sir.
Nihar,
Present, sir.
Vishnu Karthik,
Present, sir.
Gauri Shankar,
Present, sir.
Ishwar,
Present, sir.
Jay Prakash,
Yes, sir.
Present, sir.
M. Kumar,
Sir. Sir.
Krish,
Present, sir.
Ran Ajay, Noel Simon,
Present, sir.
Vamsi Krishna, present, sir.
Ish,
Present, sir.
Akshaya,
Present, sir.
Dev,
Present, sir.
Present, sir.
Al Rao,
Present, sir.
Kumar, Vignesh Krishna Madhukumar, Vedant Madhur, Anand,
Present, sir.
Vani, Vasan, Kalaipriyan, Narayanan,
Present, sir. Anish, present, sir.
Raj,
Ankal present, sir.
Keshav Kumar, Akash Kumar,
Present, sir.
Sir Keshav Kumar, present, sir.
Karthik Prasanna,
Present, sir.
Sai Kaustubh,
Present, sir.
Varun Ahalyan,
Present, sir.
Sarvesh Krishnan, Femina,
Present, sir.
Effort Gionel,
Present, sir.
Amal Manoj,
Present, sir. Present, sir.
okay. Sai Rohit,
Sir, he has texted in the chat box.
Deepesh, Sundar Krishna, Sharan Ajay, Vignesh Krishna, Vedant Madhur, Shivani, Riya Vasan, Kalaipriyan, what? I didn't get you. Repeat. Kalaipriyan. What about Shivani, Riya Vasan, Sarvesh Krishnan,
Chat box, sir.
all right. So we'll meet again on Thursday. You can leave the class now. I'll stop
Thank
the
you, sir.
recording.
Thank you, sir.
Thank you, sir.